Last time we started talking about linear programming, and we described the linear program and gave some examples on how to solve inequalities first to determine the region that satisfies the solution set of, or that consists of solution sets of an inequality of two variables, x and y. And we solved some other set of inequalities. I mean, for example, here 4 inequalities, 1, 2, 3, and 4 inequalities with 2 variables. We showed this in the last video, and we determined the solution for this set of, or we found the solution set for the system of inequalities as we did here. As you can see, this region here is the solution set. That means if we choose any point here in this set, that point will satisfy these 4 inequalities. Now this set here is called the feasible solution, or the feasible set of solutions, and it's denoted as S, capital S. Now today we'll learn a method that's called the corner method, or the method of corners, to solve the linear program. So if we have the following linear program, we have a function that we want to minimize, and we have some constraints. These are inequalities, and we want to find the solutions, or the solution set, or and then the value of, or the values of x and y, or the point that minimize the profit function, or the objective function. This function here is called objective function, and in this case it may represent the price. That's why we use capital P. So we want to find the solution xy that minimizes this function here, the objective function, using these constraints and the objective function. Now how to do that? We use a method that's called the method of corners. There are many methods to solve a linear program, but this is one of the simplest methods. So we need to know the following things. First, we want to know how to graph region S, and that's what we learned from the previous video about how to graph a set of constraints, or a set of inequalities, or system of inequalities, and then how to determine the feasible sets. The intersection of all those solutions will be the feasible set as we have here. Let me reshade it again. This region, this is called the feasible set, and then we make a table and to determine the feasible solution that optimizes, here minimizes, the objective function, and we call it the optimal solution. So let's solve this problem. We want to minimize this function p equals 3x plus 2y, and we have some constraints here. So we first graph these regions and determine the feasible set. So let's do that. We start with the inequality 2x plus 3y less than or equal 12, and then we make it an equation, convert it into an equation in order to graph the region. So x, y, or to graph the line, and then we graph the region using the inequality. Okay, so we choose 2 values. Let's choose 0, 0 here, 0 for x, 0 for y, and we find the corresponding values. So when x is 0 here, y equals 3y equals 12, that means y equals 4. And when y equals 0 here, y equals 0, then 2x equals 12, that means x equals 6. So the 2 points here are 0, 4, and 6, 0. Let's graph the other inequalities. So we have the second one is 2x plus y is less than or equal to 8, so we write it as an equation first, and then we determine the 2 points that where the line, or the graph of this line pass it through. So we have x, y here. We choose x0, y0, and then we find the corresponding values of x and y. When x is 0, y equals 8. When y equals 0, 2x equals 8. That means x equals 4. So the 2 points are 0, 8, and 4 zeros. We need 2 points in order to graph the line. Now we also have two other conditions: x greater than or equal to 0 and y is greater than or equal to 0. And actually we graphed those in the past video, in the last video. As we see, this is x is greater than or equal to 0, I mean the region to the right of the y-axis, and for y greater than or equal to 0 is the region above the x-axis. Okay, now we graph the region, so we need to graph those lines and determine the solutions. So we have 0, 4, 0, 4 is here, and 6, 0, 6, 0 is here for the first line, and then we connect them with a straight line because we have equality here. If we don't have equality, we just draw a dashed line. Now for the pink color, the first line, the pink colored line, the solution, is it above that line or below? In order to determine, we choose a point test value, like test point like 0, 0, and we see if that point satisfies the inequality, then the solution is below that line. If it does not satisfy the solution or the inequality, then the solution is above the line. So let's substitute 0, 0. When we substitute 0 here, this is 0, 0 less than or equal to 12. 0 is less than 12. Yeah, that's correct. So we just graph a little arrow to indicate the direction, or the region of the solution. We don't need to shade the whole region and then make it overlap with other solutions. We may do it this way: just graph little arrows to denote that the solution will be under this line. Now for the second inequality, 2x plus y less than or equal to 8, we start graphing the line that's associated to this inequality. So we have 2 points, 0, 8. Let me choose the color, blue color. 0, 8 is here, and 4, 0 is here. Now we graph it this way, and then we determine where's the region. Is it above that line or below? We still can use the same test point, 0, 0. So let's substitute 0 here, 0 here. 0, 0 plus 0 is less than or equal to 8. That's correct. So the solution is below this line. Now we have another two inequalities. X is greater than or equal to 0. That means to the right of the y-axis. Let's use the brown color here, to the right of this. And above y greater than or equal to 0, that's above the x-axis. So I'm going to use this gray color. So where's the intersection of all these regions? The intersection of all the regions is this region. They overlap on this region. So this is S. This is what we call S, or the feasible set, the region S, and that determines the feasible set. Now after determining this, we need to determine the feasible solution. Now how to find that? We apply the method of corners, and we call it method of corners because we only pay attention to the corners. So what are the corners in this case? We have this corner 0, 4, this corner 0, 0, this corner 4, 0, and this corner, but we don't know this corner. Now how to determine this corner? In order to determine unknown corner, we look at the lines that make this point of intersection. So it's intersection of the two lines, the pink line and the blue line. The pink line is represented by this equation, 2x plus 3y equals 12, and the blue line is represented here by 2x plus y equals 8. Now we need to solve this system. Let me solve it here. So we have 2x plus 3y equals 12 and 2x plus y equals 8. Now we solve this to find the point of intersection xy. We can use any of the methods that we learned. We can use elimination method, substitution method, Gauss-Jordan elimination method, or inverse matrix method. Any method that you are familiar with or you feel comfortable for applying it, that should work. I prefer to use the elimination method. So I want to eliminate, for example, x. So we subtract those two equations. 2x minus 2x is 0. 3y minus y is 2y. And 12 minus 8 is 4. And then y equals 2. So after finding y, we can substitute in one of the two equations. Let's substitute into the first equation. We have 2x plus 3 times y is 2, equals 12. Then 2x plus 6 equals 12. Subtract 6 from both sides. You get 2x equals 6, and then x equals 3. So the point is xy, I mean 3 and 2. So this point here, now we could find the point here, 3, 2. Now we have all the vertices that we are worrying about, because the solution will be one of these 2 points. So here we usually, when we solve linear system or linear program, we have the solution on one of these corners. So that solution will be the feasible solution, or the optimal solution that maximizes or minimizes the problem. Our problem is to minimize P, so the solution that minimize P should be one of these corners, and that's why we call this method is the method of corners. Now, how to determine which one of them? So we make a little table here, and here we put the point or corner, and the value P, 2x plus 3y. Sorry, 3x plus 2y. Now, the first point is 0, 0. We plug it here, so we find the value of P. P is 3 times 0 plus 2 times 0, and that's equal to 0. Now we plug 4, 0. P is 3 times 4 plus 0 times 0, which is equal to 12. Now the third one is 3, 2, the point that we just calculated. So P is 3 times 3 plus 2 times 2. 3 times 2, 3 is 9. 2 times 2 is 4. 9 plus 4 is 13. Now the last point is 0, 4. So we plug x equals 0 and y equals 4, and that gives us 8. Now, what is the point or the corner that minimizes the function P? That we want to minimize the function P, so the point that gives the smallest value is 0, 0. So 0, 0 is the optimal solution. So the optimal solution is obtained from the point 0, 0. Now we have some notes here. The solution of linear program occurs at a vertex or corner, as we described, of the feasible set S. And if the objective function P is optimized at 2 adjacent vertices, I mean 2 adjacent vertices like 0, 0 and 4, 0, if those give same answer, for example 0, then all points that lie on the same or on the line segment joining the 2 points vertices are solutions. So there are infinitely many solutions. Any point on that line, for example this point here, 2, 0 is a solution, and any other points here on this line segment will be a solution. Now, the third thing, or the last thing, if S is bounded, here S is bounded from above, below, from the right, and from the left. This region here is bounded. Then P has both maximum and minimum. As we can see by just looking at the table, this is the minimum, and what is the maximum? The maximum is 12. So if the problem asks us to maximize P, then we choose the point 40, because 40 gives P equals 12, which is the maximum value of the function P. Now let's take another example. Here we want to maximize the function P equals 4x plus 3y, and we have some constraints here. We want to use the method of corners to maximize P. Same thing here. We start with the constraints. We have the first condition here, 2x plus 3y is less than or equal to 18, x is greater than or equal to 0, y is greater than or equal to 0. Those two conditions here, x is greater than or equal to 0, y is greater than or equal to 0, are called the conditions of non-negativity. Because usually x and y, in many cases, they denote number of items. So number of items cannot be negative. That's why we suppose that x and y are non-negative. It can be 0, it can be greater than 0, but number of items cannot be negative. Now we graph those regions. So here we have 2x plus y equals 10, and then we make a table for xy. We choose some value for x, let's choose 0, and some value for y, and we find the corresponding values. So when x is 0, y equals 10. When y is 0, x equals 5. So the 2 points are 0, 10, and 5, 0. And for the second one, we convert it into an equation, and then we make a table, and we determine 2 points. So 0, 0. When x equals 0, 3y equals 18, that means y equals 6. And when y equals 0, 2x equals 18, that means x equals 9. So the 2 points are 0, 6, and 9, 0. Now we graph the region. This is the x-axis, this is the y-axis, and then we start with the first inequality, 2x plus y less than or equal to 10. So we graph the line that is associated to this. 0, 10 is here, and 5, 0 is here. And then we connect them with a straight line, and we need to determine whether the solution is above this line or below this line. So we need a test value, and the best test value here is 0, 0, except if that line passes through this point, then we need to choose another point, a different point. So 0, 0 is the test value here, but you can choose any test value. You can choose a point here like -1 and 2, for example, and that should work, but we choose this point because this is the simplest point. Now we plug 0, 0 here. So when x equals 0, 2 times 0 plus y equals 0 is less than or equal to 10. That's correct. So the solution is below this line. Now we look at the second, we graph the second line. So let me use the blue color. So we have 0, 6 and 9, 0, 9 on x and 0 on y, and then we connect them with straight line. Now we need to determine whether the solution is above or below this line. We choose same test point. So substitute 0 here, substitute 0, 0, 0 is less than or equal to 18. That's correct. So the solution is below this blue line. Now we look at the region where these are overlapping, but we still have two inequalities. X is greater than or equal to 0, as we described before. That's everything to the right of the y-axis. Y is greater than or equal to 0. That's everything above the x-axis. Now, where's the region? The feasible or the solution set, or the region S. This is the region S. They overlap here. Okay, now let's call this set S. Okay, so this is the feasible set or region S. Okay, now after finding S, we make a table with the point or corner or the point and the value of P, but P is 4x plus 3y. Now we choose the points. We have 0, 0, and we have 5, 0, but we have this point. This is unknown. We need to find it. We find it the same way as we did for the previous exercise. So this point comes from the intersection of the two lines, this line and this line. So we need to solve this system. 2x plus y is equal to 10 and 2x plus 3y equals 18. So let's subtract them. When we subtract, 2x minus 2x is 0, y minus 3y is negative 2y equals 10 minus 18 is negative 8. Then we divide by negative 2, both sides by negative 2. That gives y equals 4. So once we find y, we can plug in any of the two equations to find x. So let's plug into the first equation. So we have 2x plus y is 4, equals 10. And then we solve this. Subtract 4, you get 2x equals 6. That means x equals 3. So the point is 3 and 4. X first and then y. So this point here is 3 and 4. We put it here. And then we continue. We have 0, 6 as well. And then we plug these points into the objective function P. So when we have x equals 0, y equals 0 here, we get 0. When x is 5 and y equals 0, we get 20. When x equals 3 and y equals 4, we have 24. And when x equals 0 and y equals 6, that is 18. But we want here to maximize, to find the maximum value or the maximum value of P that's obtained from a certain point. So what is the point that gives us the maximum value? The maximum value is 20, and that occurs or can be attained at 5, 0. So P is maximum at the point 5, 0, and its value is 20. So this is the method of corners. Let's solve another example. We want to find the maximum and minimum, and we know from the previous note, if the region is bounded, then we have maximum and minimum. Now let's look at the constraints. So we have 2x plus 3y less than or equal to 30, negative x plus y less than or equal to 5, x plus y greater than or equal to 5, x is less than or equal to 10, x is greater than or equal to 0, y is greater than or equal to 0. Now we graph these. We convert them into equations first, and then we choose some value for x, some value for y, and find the corresponding values. When x is 0, y equals 10. When y is 0, x is 15. So the 2 points are 0, 10, 15, 0. And for the second one, negative x plus y equals 5. So we choose x equals 0. When x equals 0, y equals 5. When y equals 0, x equals negative 5. So the 2 points are 0, 5, negative 5, 0. Here, the equation is x plus y equals 5. Then when x equals 0, y equals 5. When y equals 0, x equals 5. So the 2 points are 0, 5, and 5, 0. Now here, x equals 10. We make it equality or equation. And then we graph this. When we say x is less than or equal to 10, this is 10 here, less than or equal to 10, that means to the left of that line. X equals 10 is a vertical line, and less than or equal to this, that means to the left of this line. Now let's graph the region. Now we have the point 0, 10, and 15, 0. And then we connect them with a straight line. That's the first inequality, or the first line that is associated to the first inequality. Now we choose the test value 0, 0. This is test point. And then we plug it here. 0, 0 is less than or equal to 30. Yes. So the solution is below this line. And then for the second one, we have 5, 0, 5 and negative 5, 0. 0, 5 is here, and negative 5, 0 is here. And then we graph this line. Now, after graphing this, we use the test point 0, 0 to see if this is correct. 0 plus 0 is less than or equal to 5. That's correct. So the solution is below the blue line. Now we have the third inequalities. Let's use red color. We have 0, 5 and 5, 0. Okay, I made a mistake. So let me back up here. I made a mistake. Sorry about that. The mistake was how to graph the second inequality. Negative 5, 0 is here, not on the right hand side. So okay, so for the second inequality, we have 0, 5 and negative 5, 0. Negative 5, 0 is here, and then we connect it with a straight line, and we look at the some people prefer to write the equation here that's related to each line, but since we have colors, we don't need to worry too much about this. So we use the test value here, substituted 0 plus 0 is less than or equal to 5. 0 is less than or equal to 5. That means the solution is in the region or in the side of the point 0, 0 from the line, so below the line. Now we graph the third region. The third region is x plus y is greater than or equal to 5. We need to solve this inequality. So we have 0, 5 and 5 zeros. 0, 5 at this point, 5, 0 is here, and then we connect them with a straight line. So this is x plus y is is equal to 5 because this is a line. Now we choose the test value 0, 0 and substitute it here. 0 plus 0 is greater than or equal to 5. This is not true. That means the solution will not be below this line, but will be on the other side. I mean above the red line. Okay, because 0, 0 does not satisfy the inequality of that's associated to that line. So the opposite side of that line, the opposite region, will be the solution. Okay, so now we have x less than or equal to 10, and so we graph x equals 10. Where's x equals 10? It's supposed to be somewhere here. This is x equals 10, and less than or equal to 10, that means to the left of this. And then we have the usual non-negativity conditions. X is greater than or equal to 0, and that is above or to the right of the x, the y-axis, and y is greater than or equal to 0 above the x-axis. So where's the region of intersection of all these regions? So the region of intersection is this: above the x-axis, to the left of the brown line, and below the green line, and below the blue line, and to the right of the red line. This is the region. So this is region S. This is region S. After determining the region, we need to determine the corners. What are the corners? We have 0, 5, we have 5, 0, and we have this here is, since this line is 10, x equals 10, so it's 10, 0. So we know this. But we don't know this point and we don't know this point. We have two unknown points, so we need to solve the system to find those points. I mean the systems that are related to those 2 points. This point here comes from the brown line, which is x equals 10, and the red line is 2x plus 3y equals 30. But here we don't need to solve using substitution method or by elimination method, but we can use substitution method. X is 10, so we just plug it here to find the value of y. 2 times 10 plus 3y equals 30. 20 plus 3y equals 30, and then we subtract 20 from both sides. We get 3y equals 10. That means y equals 10/3. So the point is 10 and 10/3. Okay, so this is now given, or we could find it. Now, what about this point here? This point comes from the intersection of the blue line, negative x plus y equals 5, and the green line comes from the first equation, 2x plus 3y equals 30. And then we solve this. Let's solve it using the elimination method. So if we multiply the first equation by 2, we obtain negative 2x plus 2y equals 10. We multiply each term by 2, and then the second one stay the same. Now we subtract, or we add them. We have negative 2x plus 2x is 0. 3y plus 5y plus 2y is 5y. 10 plus 30 is 40. And then we divide both sides by 5. We get 8. So y is 8. Now how to find x? So we can plug into the first equation. So we have negative x plus y equals 5. Subtract negative 8. You get negative x equals negative 3. That means x equals 3 by dropping the negative signs from the left and the right of this equation. So the point is 3 and 8. X is 3 and y is 8. So this point here is 3 and 8. And then we make a table. So we have the points or corners and P. P is 2x plus 3y. Now the points are 5, 0, 10, 0, 10, 10/3, 3, 8, and 0, 5. We have 5 points. Now we plug them into this equation, or this function P. So we have 10 here. When we plug 10, 0, we get 20. When we plug 10 and 10/3, we get 2 times 10 plus 3 times 10/3. And we can cancel 3 here. We get 20 plus 10, which is equal to 30. Now we plug 3, 8. We have 2 times 3 plus 3 times 8. This is 6 plus 24, which is equal to 30. And then 0, 5, that is 15. We want to find the maximum, I mean maximize. This is the max. And we want to minimize, this is the minimum. So the minimum occurs at the point 5, 0, and the maximum occurs at each point on the line segment that connects the points 0, 10/3, this point here, that connects this point here, and the next point 3, 8. And as you remember from a previous note, if the maximum or the minimum occur at 2 points, two adjacent vertices, then all points on that line segment will satisfy the maximum. The maximum will be any point on that line segment. So it will be all points on the line segment that connects the point 0, 10 and the point 3, 8. Now the last question, if S, let's start with a note. If S is unbounded, it might be unbounded from above or from below, or from the right or from the left. Now the coefficients A and B, those are, in the previous example, for example, they are 2 and 3. Those are non-negative. And the constraints include x greater than or equal to 0, y is greater than or equal to 0, then P has a minimum value but does not have maximum value. So let's see. We want to use the method of corners to solve the following linear program. We have the objective function here, we want to minimize it, and we have some constraints here. Now first, let's look at the conditions. We have A and B are positive. A is 1, B is 2. But we want to see if S is bounded or unbounded. So we need to graph the constraints first. So negative 2x plus y less than or equal to 4. And we have x minus 3y less than or equal to 3. X is greater than or equal to 0. Y is greater than or equal to 0. We convert this into an equation. And then we find the 2 points. When x equals 0, y equals 4. When y equals 0, x equals negative 2. By dividing by negative 2, we get negative 2x equals 4, x equals negative 2. The 2 points are 0, 4, and negative 2, 0. Now for the second inequality, we convert it into a 0. We convert it into an equation. So we have x minus 3y equals 3. And then we make a table, the table xy, we have 0, 0. When x equals 0, y equals negative 1. When y equals 0, x equals 3. So the points are 0, negative 1, and 3, 0. And those are, we know how to graph those. Now we graph the region on the xy plane. We have, let's use the same thing, the red color for the point, the first inequality, or for the line of the first that's associated to the first inequality. So we have 0, 4. This is 0, 4, and negative 2, 0 is this, and we connect them with a straight line. So this is negative 2x plus y equals 4. And then we want to see if the solution set is to the right or below or above this line. We test 0, 0. When we plug it here, we get 0, 0 is less than or equal to 4. That means yes, the region will include the 0, 0, I mean below that line. And then we graph the second line. We have 0, negative 1, and 3, 0. Here we have 3, 0, and then we connect them with a straight line. This is x minus 3y equals 3. We want to check if the solution or the region is above this or below this line. So we test 0, 0. 0 minus 0 is less than or equal to 3. So that means, yes, it's correct. So the solution will be below this line. It's below the green line and below the blue line. And we have x greater than or equal to 0. That means to the right of the y-axis. And y is greater than or equal to 0. It's above the x-axis. I mean here, above the x-axis. So the region, the intersection will be this region here. Now this region here is to the right of the y-axis and above the x-axis. And it's below the blue curve or blue line and below the green line. So this is the region. But if you look at this region, it's bounded from the left, below and above. But it's not bounded here from the right. It's not bounded. So S is not bounded. S is unbounded. So P has a minimum value, but it does not have maximum value. So we have this point here, but we don't know the maximum value. We have minimum value. This is the minimum value. It occurs at 3, 0, when x equals 3 and y equals 0. P is x plus 2y. So P equals 0, x is 3, so P equals 3 plus 2 times 0, which is 3. So P equals 3. This is the minimum value of P, and it occurs at 3, 0, but we don't have maximum. No maximum because it's not bounded. So for the linear program, can we maximize? No. The reason is that we don't have points here to be, it's not bounded from above, so we can't find a maximum point.